Okay, so let's consider one more, and then we get into the active circuits, which is used in all the feedbacks. But it's a similar situation. So you could see that again. We're going to look at C1, R1. We're going to look at C2, R2, and C2. And again, this is the output voltage and the input voltage, and it's always assumed S because it's a frequency. So we could see from this, there's going to be two separate things. First of all, at low frequency, remember the capacitors are going to dominate. These capacitors will dominate. So what will happen is at low frequency, the reason why they dominate is this is going to be high impedance and this is a series circuit. So in the series circuit, the high impedance dominates. So at low frequency, the C2 dominates, and at low frequency, the C1 dominates. So you effectively have these two capacitors in parallel. I mean, as a capacitor divider. Okay, so that means the capacitor divider is going to be C1 over C1 plus C2, and that's what you're going to have. Now, depending upon what comes first, the poles or the zeros. So you're going to have either a pole and a zero occurring, or you're going to have another circuit where you're going to have the C1 and over C1 plus T2, so he's going to start there. And then if you're going to have the zero first, then you're going to have the pole. So this is the one that's the pole first and then the zero. And this is going to be with the zero first and then the pole. Ultimately, what is this? Again, these are going to end at the same point. Why? Because high frequency, the X of C2 is a short, and the X of C1 is a short. So you're just going to have an R2 over R1 plus R2. So both of these are going to end off at R2 over R1 plus R2. They'll be both the same, R1 over R1 plus R2. Just in between, the values of these individuals will determine if the pole or the zero comes first. So therefore, looking at the plot, you could see that the output over the input transfer function, looking at this, is going to be that gain term, like the K, like before, C1, C2, and then you're going to have your SC to R2 plus 1 over your S C1 parallel C2, and you have your R1 plus R2 plus 1. And that's your transfer functions. And you could see they'll work out pretty good because at low frequency, when S is 0, you have just this ratio. That's these. And then if the pole comes first, depending upon these values, you're going to have the pole coming first, then the 0. At high frequency, you could see that these are going to go out. The C's are all going to go out. The S's are out. And all you're going to have is R2 over R1 plus R2, which is at these values right here. Okay? So that's the last one I want to play with, because a lot of times we're going to really look at mainly active circuits. Okay? What we're going to do is there's going to be some simulations. I'm going to simulate this again like I did before. And you could see the poles and zeros. You could see, we'll see how they move. The nice thing about the LT Spice is you can place these values in and you can see how they move around, and you'll see that they follow these shapes. Okay? So now that we looked at the passive circuit, let's look at the active circuit. That's just actually the active circuits I find is kind of much easier because you're going to have an AC virtual ground, and you're going to have just the impedance transfer from the output to the input. It's output over input. So let's look at op-amp circuits where you have R1 and you have the negative terminal feedback, and you have RF, and you have a simple feedback where you may have a reference here, but AC ground. So normally you'd have a DC reference, and this is Vref, which it could be 1.25, 0.8 volts, 2.5 volts, but for AC, it's a short, because for AC, a DC is a short. Okay? And so now we're going to input our input. We're going to call that Vx hat. Hat is going to be standing for the AC inputs, and then we're going to call this a VC hat. And you'll see why we do that later when we do the feedback. So basically, into the op-amp is going to be this impedance divided by this impedance. So the output over the input is going to be, now forget the minus. We know it's a minus. It's inverting. So, I don't always have to keep putting a minus in here. We know it's an inverting input. The input goes up, the output goes down. It's inverting, understood. So this is just RF over R1. And that's the transfer function, and it's a constant. You've got 20 log, it's going to be a straight line, 20 log. Okay, if RF is 10 times bigger than R1, we have a gain of 10, 20 log of 10, 20 dB. Okay? The next step is, hey, can we create a zero? So this just looks like a curve that goes like this, and this is RF over R1, and if RF is bigger, then this is 0 or 0 dB, and if we look at 20, we're looking at 20 log of this, and then this is whatever the gain is. Okay, assuming here RF is larger than R1. If RF is less than R1, you're going to be below. It's going to be... Instead of a gain stage, it's an attenuator stage. Okay, so the next section, and again, there is no phase. The phase angle is 0 because it's real. There's no frequency dependent. So the next circuit we're going to look at is, how do we create a 0 out of this? Okay, so all we have to do is stick in a capacitor in parallel with this R1. And let's see if it just intuitively makes sense. Again, this is AC ground, this is the Vx, and this is your VC hat. And this is RF. Again, in your DC, we're going to have RF over R1, because this is going to be infinity, the capacitance. Capacitive reactions at 0. So we're going to see that we are going to have this gain RF over R1 at low frequency. Now, when this impedance is equal to this impedance, what winds up happening? Now, as the frequency goes higher and higher, this impedance is starting to short out R1. So that means this is moving up. At that point alone, we have 1 over 2 pi. That's one CS R1. And that's that breakpoint. And since it's going up, we know it's a 0. And it keeps going up forever. Okay? Of course, ultimately, it'll see poles of the op-amp and stop going up. Okay? But for all intents and purposes, this is what we have. Okay? So what is the transfer function of this? The transfer function of this, assuming that we always are negative, so we forget the negative sign, we have RF over R1, and this is the 0, which is the SCS R1 plus 1. And this impedance is here. So that you write it out, say just like that. So you can see there's your gain. Now your phase, since this moves up, your phase here is going to be plus, and it's the arctangent of what this frequency, we're going to call that a 0, and it's F over F0, and you're going to see it starts off at 0 degrees at very low frequency and goes all up to plus 90 degrees when F is much greater than Fz. Okay? So it's not good to have a circuit that keeps raising up like the last circuit here that we have, that keeps growing with frequency here. Because the issue is noise. As this keeps going up, your gain is going up. This is a gain. This is the output over the input. Since the input is going lower and lower, your output is going higher and higher. That means any signal noise at high frequency is going to be amplified. It's going to be way up there. So this is a very noise-sensitive circuit, and you never want to have a circuit like this. So what you have to do is you have to stop it from going up. Now, how do you stop it from going up? You add a series resistance to the capacitor. So you stop it from going up. Here you always know that R1 should be much greater than R3, so that it doesn't play a role initially, but at a higher frequency it does. So this is the circuit that I'm looking at now. And now we have RF, and we have again Vx hat and Vc hat. So now we have, looking at the transfer function, again, I don't need to derive all this stuff. I can see what's happening. You draw it. What happens at low frequency? You have this over this because the capacitor is open. So at low frequency, you have the gain RF over R1. Now what happens is, just like before, this capacitor reactance starts to hit this first because, like I said, R1 is much greater than R2. So this impedance, C sub S, impedance is going to reach R1 first. So when it does, it moves up. And that's 1 over 2 pi CS R1. Now when it goes up here, and it's of course actually this plus this in reality, but again, if R1 is much greater than R3, it's approximately R1. But for all intents and purposes to be a perfect equation, we have this, because when you look at this, it's these in series. Now, how does it stop going up? It keeps going up until when? Until this capacitive reactance is equal to R3. Then what happens at higher frequency, this becomes a short. This capacitor becomes a short, and it puts R1 in parallel R3. That is that breakpoint right here, and that is 1 over 2 pi, and that's when CS is equal to R3. And up here, this value now looks like a circuit where this is a short, and it's RF over R1 parallel R3. So a lot of times you could draw some circuits to say, hey, what does this circuit look like? That circuit looks like a simple thing of R1 and RF at that point right here. And what does this circuit look like here? Well, that circuit also looks like a fixed point where this is RF, but this here is R1 parallel R3. Put those two in parallel, and this is at high frequency. This is at high frequency. This is at low frequency. And in between, you get this. Okay? So you could see then, right away I can write the transfer function. The output Vc to the V sub x is what? This gain here. You know it's RF over R1. You know that this is a pole. That's on the bottom. That's S. Just write this down. CS R1 plus R3 plus 1. What's on the top? This 0 right there. S. CS R3 plus 1. You see, that is your equation. Very simply, let's see if it works. At low frequency, when S is 0, the top is 1. When S is 0, the bottom is 1, and it's RF over R1. That's the same here. Then at high frequency, what we have is up here. We want to see that. Well, that means that SCSR3 is much greater than 1, and this term is much greater than 1. So you forget the ones, the SCs cancel out with each other, and look what you got. You got RF and R3, and you got R1 bottom, and you simply got the parallel combination when you flip this to the bottom of RF over R1 parallel R3. Okay, so these next two circuits are kind of some of the most important circuits that you'll see. One is going to be used for current mode programming compensation, and the other is going to be used for voltage mode compensation. So here's an R1, and what we're going to wind up having is I want what's called an integrator, and that's C of F, and this is RF, and a 0, and that's what I want. And this circuit's going to give me that. What's going to happen is this. At low frequency, this capacitive reactance is going to dominate. And in Laplace, this is 1 over S C of F. That's the X sub C. So therefore, the impedance, of course, is this divided by this. It's always that. It's this top divided by bottom. But at low frequency, this capacitor reactance is so much higher than RF, it takes over. So what we have is a curve that looks like this, which is 1 over SCF R1. And that's your gain. That's what's called an integrator. It pulls it down. Then all of a sudden, when this capacitor reactance is equal to R sub F, it stops going up. And the gain here then is RF over R1. So if you look at circuit-wise, this looks like a circuit that looks like this. That's what that looks like. So you could see that the gain is this over this. This circuit at high frequency looks like a circuit like this, where C sub F is shorted. And it becomes RF and R1. So you could see the gain is this over this, which is exactly that. And the break point is again when the capacitive is equal to your RF. And that break point is 1 over 2 pi CF RF. Now we just draw the equation, the output over the input, straight line from the transfer function. We could see it starts off with the DC value of this, so this is what we start off with. And then what? We add a 0, and we add a 0 by multiplying that, which is CF RF plus 1, and that's it. That's our transfer function. Now let's see if it matches. At low frequency, this is a 0, that's a 0, and you can see the gain is infinity. Well, of course, the gain keeps on going up to infinity, but as we really know, what happens here is there'll be a op-amp gain limit, and that'll be the pole of the op-amp. That'll set the high gain limit, and because no op-amp is going to have a gain of infinity. So that'll be the op-amp gain. But you don't see that in the external circuit. That's internal to this. Okay? So, and by the way, there is a course that I will be teaching also on op-amp design and IC design that covers all these different internal workings of the designs of ICs pertaining to switch mode power supply. We design a whole switch mode power supply using IC designs. Both a buck, a boost, a flyback, all kinds of stuff. Okay, so that's a cool circuit, and a lot of times this is used for current mode programming. And you'll find out later that you will have a single pole roll-off with an ESR 0, and you'll normally put the pole, you'll put the 0 here to cancel the dominant pole of the power plant. But that, we're getting ahead of each other. That's feedback, and we're going to get that a little later. The last circuit I want to discuss is voltage mode control, and we're going to do a lot of stuff on this. And this circuit is very, very, very popular for, of course, voltage mode control. In voltage mode control, just like we had before, you see we had two poles in the plant. I call the power stage where it's the converter, the buck, the boost, the buck boost. That's your plant. And we had two poles. And therefore, we're going to need two zeros to cancel those two poles. And we need an integrator to be a straight line. Because always in feedback, always we want a straight in feedback. Ultimately, our loop gain, we always want a straight line. Again, we're getting ahead of each other, but that's okay for right now. We always want our whole system to be some k prime over some s. And k is going to be a different constant than it's the constant around the loop. Okay, so right away we have this system right here. So let's look at the transfer function. Again, what do? We start off at low frequency, where this is 1 over SCF. And at low frequency, this is very high, which means this impedance is much greater than this, so it looks like a capacitor circuit. This impedance, again, is also high, but and high impedance in parallel with a lower impedance, R1 wins. So let's look at something. Typically, R1 is going to be much greater than R3, like before, because we're going to want the zero to come later, and then we're going to have also CF is greater than CS. Okay, knowing those conditions, what do we have? We have an integrator who's 1 over S CF R1. So what I'm going to do is I'm going to start on a fresh page to draw this out. Okay? So what we have here is, like I said, S CF R1. The next thing we have is going to be, it's going to stop, okay? And when is it going to stop? Well, let's draw the circuit out again, so it's important to see what's going on from the circuit point of view. Okay, everything is a circuit point of view. That's what I kind of like. Everything is real circuits that we're dealing with. Okay, so when this impedance is equal to this impedance, that's when it will stop going down. So that point is when 1 over 2 pi CF RF. That's the frequency that'll stop, and that's your first zero that you'll say. Because this is an integrated, it stops going down, it means it has to be a zero to make this stop. Next, what's the next thing? As we had before, you see, since the R1 is much greater than the R3, then this is going to occur first. The zero is going to see this plus this. So that is the next stage. So at this point, you've got to understand, at this point, what is the circuit? Always draw the circuit which it looks like, and that'll really help you with this. So this becomes C sub F, and this becomes R1, and this is Vx. See, right away, you could see the gain is just this over this. And how do you write this in capacitor, in impedance form? It's 1 over SC. That's why 1 over FC divided by this, it becomes 1 over SCF R1. That's this. So you see, that is this circuit right here. What does the circuit look like here? Well, as we said the capacitor now is lower than RF, so RF dominates. It's a series circuit, and we have a circuit that looks like this, because the C sub S did not come in yet. Okay, so that's what this circuit looks. So the gain is RF over R1. Now, what happens when the C sub F is equal to R1 plus R3? It starts moving up again. That's your second zero. Why? Because this impedance is getting lower. It's in parallel with this. It's pulling this lower. And that is an SZ2, we'll call it. And that is 1 over 2 pi CS, and that is R1 plus R3. Same thing almost like before. Then it keeps going up and up until when? Until this capacitive reactance is equal to R3, which then stops from going up. And that point, of course, is a pole because it stops from going up. Now, that's going to be 1 over 2 pi CS, R3. Now, what is that gain? Remember what the circuit looks like at the high frequency. That means all the capacitors are shorted. So at high frequency, what you have is RF, because that CF is shorted, and you have R1 in parallel with R3 because the CS is shorted. Small compared to R3. So at that point, that's what the waveform you look like that you have here, and therefore you know what your gain is. It's this divided by the parallel combination, so therefore it is RF over R1 parallel R3. Again, directly from the plot, I will derive the transfer function. Now you could do this in math, knock yourself out, but you got a bunch of pages. Here I just draw a picture and boom, I get the transfer function. Now, where do I begin? Look at your waveform. There's my DC, so write it down. Okay, now, what's my first zero? Right here, right there. So write it down, SCFRF plus 1. So easy that is. Now, where's the second zero? Right there. Write that down. There's a second zero. SCS R1 plus R3 plus 1. Okay, what's your pole? It's right here. That's your pole. Right there. The poles are on the bottom. And that is SCS R3 plus 1. Great. That is your transfer function. Very quick. Just from a picture. Now, when you get used to this, I draw this immediately. I just draw the waveform just instantly and are able to put my poles and zeros. So you can see at low frequency when S is much less than 1, this is 1, this is 1, this is 1, and you have this. That's this circuit coming down right here. That's this. So it follows. Then in the mid-frequency, what's the mid-frequency? Well, this point is when, at this point here, is when the C sub F, RF, is bigger than 1. But this is still smaller than 1, and this is still smaller than 1. So you get this circuit over this circuit, and you can see the SCF and SCF goes out, and you have RF over R1, and that's exactly what you have at mid-frequency. Then you go back and look at your high frequency. And you see at high frequency that all this is much greater than 1, this is much greater than 1, and this is much greater than 1. So you can see you have two S's on the top, two S's on the bottom. You can see they cancel out. The CF on the top, the CS and the CS, and look what you got. Ultimately, at high frequency, we'll pop this in here at high frequency so you can kind of see it very quickly. You can see you have 1 over SCFR1, and you have this is SCFR1. Remember, that's much greater than 1. That's CSR1 plus R3. Okay, remember there's no plus 1 because it's greater than 1, and we have the last one, SCSR3, and that's it. So this is, R1, that's RF, that's this one, that's RF. So you can see this goes out with this goes out with this, and we have what? We have RF, and we have R1 times R3, and this is on top, R1 plus R3. Well, do a little algebra, and what do you have? You have basically RF over R1 parallel R3, and that's exactly what we have up here. So that's our transfer function, and you can see your phase immediately, and we'll, like I said, we'll be putting this in the LT spice, and you'll see that the phase, right away I have a pole, an integrator, and that's going to give me a minus 90 degrees immediately. And then what are we going to have? A 0 to start canceling a phase, so we got a phase boost. We got another phase boost, and then we got a phase lag. So ultimately, all the phases are going to start at minus 90, back down, back up again, and we're going to be at a phase here again. So this is going to be phase circuit, and you'll see it when we simulate it. That's going to start at your minus 90 degrees. It's going to start boosting up at you, depending upon where the poles or locations are, and then it's going to start backing down on you again, okay, because the higher frequency pole.